The next topic is quadric surfaces. Quadric surfaces are the graph of a second degree equation in three variables. And I have two examples here of equations that would generate quadric surfaces. And the idea is that we want to look at equations of this form and understand which member of the quadric surface family we're working with. Now, a way we can lead ourselves to the idea of quadric surfaces by thinking of them as the three-dimensional version of the conics, the graphs of secondary equations in two variables. And so in two variables, we've looked at equations that had this form: ax squared plus by squared plus cx times y plus dx plus ey equals some number f. And the idea is the a, b, c, d, e, f are just constants. But regardless of the value of these constants, we have this general form that could represent all of these second degree equations. And so depending on the values of a, b, c, d, e, and f, the signs and the values, they might lead to different curves that we're familiar with. So some examples would be x squared plus y squared equals 4. That matches this form. This is when a is 1, b is 1, and c, d, e are 0, and f is 4. So it fits this family. And of course, we know that to be a circle of radius 2. But what if I looked at 2x minus 2 squared plus y squared equals 4? This is just kind of a little extension of this family. It's that same idea of a circle, but when we multiply the x squared by some factor, like this factor of 2, we're stretching it in one direction to get more of an ellipse shape. And then when we look at x minus 2 squared instead of x squared, we're also shifting it away from the origin, so it doesn't have a center at the origin anymore. And all these kind of make up a little subfamily of ellipses. What about some other members? What about this one? X squared plus y equals 4. So now I have still a second degree equation, but only one of my variables is squared. Or I could look at x plus y squared equals 4. And that second one might be a little more familiar, but basically these are generating some parabola shapes. And then lastly, what if I looked at x squared minus y squared equals 4 instead of plus y squared equals 4? In this case, we're going to generate hyperbolas. And the one thing to remember about hyperbolas is the value of this constant on the right hand actually tells us a lot about the nature of the hyperbola. So I'm going to look at that real quick. So here, I can use contour plot instead of contour plot 3D to plot these curves. So I'm going to look at the graph of this hyperbola, x squared minus y squared equals 1, and just play with this value of 1 a little bit. So if I make this value a little bit smaller, if I go to 1 to say half, you can see how that hyperbola is changing. I'll make it even smaller. And so the next question will be what happens when it's equal to 0. Now I have these values touching here. I basically am generating two different lines now. And what happens if I go negative? Negative very small would go like this. And you can kind of see the trend as this value gets bigger. And so you can kind of see how changing that constant kind of guides me through this little flow of the different hyperbolas. Okay, so that's a real quick recap of the conics. And now we want to extend this idea of looking at secondary equations, but now in three variables. And that would give us our quadric surfaces. Okay, so our quadric surfaces also have this general form. And all we're doing is adding in these third variables. So now I have a plus cz squared. And now I have more mixed terms because I can have mixed terms with z's in there. And then I have a I to the z power here as well. Now one thing that I want to talk about this form is that up here, when we looked at the general form for the secondary equations, these coefficients really were the deciding factor about which shape we were actually looking at. If I change the value here and include x, y terms, all this is going to do is twist my curve a little bit. It's going to change the orientation of my curve a little bit. Now, values over here, all these are going to do is give either vertical or horizontal shifts to my surfaces. So when I add these x and y terms, it will just take my circle, for instance, and just shift it in one direction over here, or maybe up here. So really, when I want to talk about which actual curve I'm working with, these are really the terms I'm looking at. And the same is true for the quadric surfaces. These are going to affect my orientation. These are going to determine where I'm centered at. And these terms are really the ones that are going to tell me about the nature of my shape, of my surface. So I'm really just going to focus in on those square terms and those constant values there. And so if I focus on those, I pretty much have ax squared plus by squared plus cz squared equals to some constant. And I want to see what happens when a, b, and c are positive or negative and how they change. And really, I can look at this as an extension of this two-dimensional case. So now let's go back up to our contour plot 3D here and put in some values. So let's look at x squared plus y squared plus z squared equals some number. All right, so where I had x squared plus y squared equals 4, I got a circle. Now I add the z squared term, and I get a sphere. So that makes sense. And just like my circle, if I take this and scale it by some value, I'm just going to stretch my surface in one direction, and I'll have an ellipsoid instead of a sphere. Similarly, if I, instead of square x, if I square x minus 2, all I'm really doing is moving that ellipsoid in one direction. I'm doing a little bit of translation. So in general, when I have constants times x squared plus constant y squared plus constants times z squared, these are positive constants, I'm going to get this ellipsoid family. Now for 2Ds, the next thing we looked at is having one squared term and the other one's not squared. So for instance, I could do something like this. And what kind of shape would I get here? Well, the two-dimensional case gave me paraboloids. What's going to happen in the three-dimensional case? Turns out I'm going to get paraboloids. And they're really the three-dimensional extension of the idea of parabola. And now we can kind of generate this shape once again if we looked at the cross sections. So if I have an equation that looks like x squared plus y squared plus z equals 4, I could say what happens if z equals 0. I would get this equation, which gives me a circle in this plane. And as I shifted my plane up, x squared plus y squared plus 1 equals 4, or if I subtracted that 1, I would get equal to 3. If z is equal to 2, I would get x squared plus y squared equals 2, so on and so forth. So I can see as I move vertically, the radius of my circles decrease. And I can see that's true also from my picture here. Now, what if I change some of the signs? Well, I could certainly just change a sign here. And if I change the coefficient of z term, you can see I just have changed the orientation of my paraboloid. Now it's opening upwards as opposed to opening downwards. So we have this direct jump from parabolas in 2 space to paraboloids in 3 space. What about the next one? The next one was changing the sign here. So instead of looking at plus z squared where we had spheres, now we're going to look at what happens if we add a minus sign here. And we get this interesting shape. And just like with hyperbolas, we're going to get a couple different shapes here. It's going to look a little different if we change this constant value of 4. So just watch what happens when I adjust this constant. I have a value of 1, and just like before, I'm going to make this thing smaller. And these are going to be hyperboloids, and they're going to call these hyperboloids of one sheet because it's really one giant surface here we're generating. But if I go to 0, I basically get straight line edges here, and so this is going to generate cones. Now I have a cone. If I go negative, I actually have a gap in between. And so this is going to be a hyperboloid of 2 sheets. So these are basically the extensions of the hyperbolas from 2 space now into 3 spaces. And I'm going to get hyperboloids of either 1 sheet or 2 sheet, or that case when the constant is 0, I'm going to generate cones. All right, so we've covered quite a few surfaces, and your book does a great job of summarizing these in this table. Now, I really want to stress here is that you have this table to look at, and you can certainly take the time to memorize the different names here, but you should also be able to sketch what these look like as well. So if you grabbed any one of these equations and said, okay, what happens when z equals 0, when z equals 1, you should be able to generate the curves of the cross sections and kind of sketch these guys out. All right, so now that we've talked about when we have these equations in standard form, we're able to sketch and really understand which surface we're dealing with. But what if they're not in standard form? So the next topic will be taking just a general second degree equation in 3 variables and trying to put it into one of these standard forms.